Hello, everyone, and welcome to today's graph reading group.
Well, we talk about unsupervised learning of invariant and equivariant representations. So if you want to join in exciting sessions like this in the future yourself, the details are in the description. Let's go.
All right, let's start.
All right. So, well, first of all, thanks so much for giving us the opportunity to talk about our recent work. I don't know if I need to reintroduce myself, but maybe just in one sentence. So my name is Marco. I'm a physicist by training. I'm since 2.5 years in the machine learning group at Bayer, based in Berlin. And yeah, so today I will take on the first part of our paper, which was accepted at NeurIPS 2022 this year, and Robin will take over the second part. So this is a work which was done in collaboration with Tuan, which is also, I think, in the audience today, and Frank from FU Berlin, and Occo, which was the lead of the machine learning group in Berlin. So okay, let's see. Right. So so the motivation behind this work is that we want to deal with symmetry in a smart way, right? Why? Well, symmetry, whether you like it or not, is part of the real world data. And in the past, especially also for neural network deep learning, incorporating symmetry in an intelligent way as an inductive bias has led to several advances. If we can think of CNN incorporating translation equivariance, message passing neural network for a permutation symmetry, and then you avoid problems like you need less data for training, you don't need augmentation, at least with respect to that transformation, and the idea is that the neural network can just focus on the signal you actually want to learn and doesn't need to deal with all the extra noise that comes with the transformation. The fact is that often I keep talking about signal, right? I mean, the label, or more general, if we think about representation learning, the signal is invariant with respect to a group of transformations, right? But the representation in which the data is presented to us is not, right? I mean, and this is the key theme of today. And before I actually describe what's the problem and what we are trying and how we're trying to solve it, I apologize, but I think perhaps it's useful to just get like a few definitions out of the way of the main concept that would be the protagonist of the talk today, so that we all on the same page. And this is too basic. I really apologize, and I promise I'll be fast. So we're talking about groups, transformations, and sorry, symmetry as transformation, and the main actor here are groups. So what is a group? A group is actually a set together with an operation, which we call the group product. And this operation needs to satisfy a few properties. So it needs to be close, means that if we multiply two elements of the group, it needs to stay in the group. It needs to be associative. It needs to have an identity element, so that the element that doesn't do anything, right? And then we need to have an inverse, means that given a certain element, there's the inverse that brings us back to the identity, right? I mean, and groups are basically they appeared in all kinds of branches of mathematics to describe number system, to describe symmetries of object or spaces, or more in general transformations. The thing is, though, groups themselves are abstract objects, right? I mean, they are sets. And what we actually most of the time are interested in, especially if we think about data, is how groups act on specific algebraic or geometric spaces, right? And especially if we think about deep learning, often we deal with, we assume that things, data live in some vector space, right? I mean, so we're thinking, okay, how does a group act on a vector space, right? I mean, because the group itself, as it is, it cannot, right? I mean, the group is just some abstract thing that can only act on itself, right? And so this bridge between the group and the action on some space is given by representations. So what are representations? So representation of a group G on a vector space V, so we need to specify both the group and the vector space, is a group homomorphism. Homomorphism in general means that we have a map that preserves some structure. So in this case, it's a group homomorphism, so it preserves the structure of the group. And this map is a map from the group to the general linear group of the vector space. So if you want the group of n by n being the dimension of the vector space, invertible matrices, right? I mean, and this map assigns to each element of the group a linear map, right? I mean, a matrix, a linear map, we can think it as a matrix, right? And such that we have the group structure which is preserved. So multiplying the element and then sending it through the map is the same as computing the representation of the separate element and then multiply them, if you want, as matrices, right? So this is the formal definition, and we can look at just a very simple example to maybe have a more intuitive view on this. And let's consider two triplets of real numbers. Right, so we have this element over 3 and this other element over 3, and if I don't tell you anything more about this, or in other words, for example, if we give this to a neural network, these two objects are basically the same. There's really no way to distinguish, okay, this triplet of number from this triplet of numbers. But of course, I could tell you, well, actually, this is just a collection of stuff like, the energy of a system, the volume of a system, and so on and so forth. Well, I could tell you, well, this triplet instead is, for example, might represent the 3D coordinates of something, or the forces, or some velocity, right? I mean, so what we usually would call a vector. And so then intuitively, we know that this transforms differently, right? I mean, these quantities do not transform, for example, if we take rotations. And so you say, okay, if we apply a rotation, they stay the same. So if you want, they transform with the identity matrix. While if we rotate a system, then stuff like, vectors rotate. And so even though the vector space in this case, R3, is exactly the same, the representation is actually different. Okay, so here is actually like 3 copies of the trivial representation, while this is a specific representation of the rotation group of SO3. So basically, in other words, so representation tell us how to interpret the data with respect to a certain group. So or in basically the same way, another way to put it, how the data transform with respect to the group. Okay, so the last bit is, okay, given all of that, what is the formal definition of equivariance? So here we have that a map from 2 vector spaces, V and W, is G equivariant if this diagram commutes, which means that, if we apply the map and then the transformation, again, we need to use the proper representation now here for the vector space W, is the same as first applying the transformation in the vector space V and then applying F. In other words, right, I mean, this commutes means that, a little bit naively speaking, that F commutes with G, right, for all the G. And then we don't need to go to the examples in details, but for example, we see that if we take, for example, here, these 2 representations to be actually the trivial representation, we see that actually this equivariance reduced to invariance. So we can think also of invariance as a special case of equivariance. And in this other example, we can see, for example, if we take F to be the translation in 3 dimensions and G, the group G, to be a rotation SO3 in 3 dimensions, we see that basically actually this diagram does not commute. So when we say equivariance, just a kind of a heads up, we need to be precise and always say with respect to what, right? I mean, it's always like a specific map with respect to a specific group. So this is basically the statement that translation and rotation do not commute in 3 dimensions, right? From the point of view of equivariance. Good. So now we are done with the basic concept. So what we want to do. So I don't need to. I think I don't need to justify in this round that representation learning is important and all the kind of application that can be used for, and that autoencoders are a really powerful machinery to do representation learning, right? I mean, but the question that motivates us is that, okay, we want to do representation learning using autoencoders because it's a very successful and powerful machinery. Can we do, but we want to do it invariantly, right? I mean, we imagine to have a problem in which we have some invariant signal, so we want to extract that invariant signal, right? I mean, so we want our bottleneck to be invariant. But the question is, okay, but what if we want to do that? We want to just learn, let's say, from raw data, right? I mean, so from data which is not itself invariant. So we don't want to extract ourselves invariant features, right? We want to use the full power of the data, but at the same time, learning an invariant bottleneck. The problem with that is that when the data representation is not group invariant, the typical reconstruction loss, right? I mean, we have X the input, X hat the decoded output, right? I mean, but if we go to an invariant bottleneck, if we transform the input, the output will stay the same, right? I mean, because since we filter out all the group action, right? I mean, so we have a problem. So the loss is not invariant with respect to group transformation, which is an issue. Okay, so how do we solve this? So this cartoon kind of shows a little bit nicely, really, the problem that we are dealing with. So here we organize the data space X is a collection of orbits, meaning, right? I mean, given a shape, in this case of fruits, right? I mean, we say, well, and the group in this case would be SO2. We can say, well, the orbit is basically all the possible poses, all the possible direction that we obtain by acting with all the group elements on a specific orbit, specific element of an orbit, right? And the fact that our encoder is invariant means that all the elements of the given orbit are mapped to exactly the same point in our bottleneck space Z. Okay, so good. So now imagine that our decoder is perfect, right? I mean, it does the job at its best, right? The best that the decoder can do is getting the shape right, but there's no way it will get the orientation right. I mean, at most it can map to the right shape in some orientation, right? I mean, but there's no way the decoder can know, right? I mean, which of these points this image came from, since they all are mapped to the same point in the bottleneck space. Meaning that the best the decoder can do is saying, I can decode to a element in the orbit, one of them, right? I mean, and it will all be the same, right? Because all the points will be coming to the same point in the embedding space, meaning that there's, so the best I can do is say I map to, so this is the decoded, right? Eta is this function, delta is this function, and this is the decoded element. At best, it can be an element in the orbit, meaning there's a group element that connects the two, right? In this case, there's a rotation that connects the two. Okay, so how can we solve then this problem? And our approach is to say, okay, so up here is basically what's here on the left, right? I mean, the invariant autoencoder. And our idea is say, okay, we want to learn an additional equivariant function, which we call psi, whose job is exactly doing what the decoder cannot possibly do, which is getting the orientation right. Meaning that, so the job of psi is to say, right, I need to predict from the data the group element that does exactly this matching between input and canonically decoded output. So so the decoder will always decode this one, and according to the input, psi needs to predict exactly the right transformation that brings us back to the same point at the beginning. And now it's important that this is equivariant, because now we can write the new loss. Basically, the new loss will be, okay, we have the input, and now we have the output to which, you know, we apply this transformation predicted by psi. And now it's, you know, basically x hat is invariant, x is equivariant if we transform the input. Now also this is equivariant, so these two transformations then cancel off, right? I mean, this is what was written here. If we transform the input and psi is equivariant, this comes out, and basically this cancel off, and now we have that the loss is G invariant, exactly what we want. And so basically, the point of the paper is showing that, you know, this actually works in practice, also to characterize how we can design such a map psi. So I'm not going to go too much into the into the meta details of the whole construction, but at least I want to give a flavor of how we came about to designing this function, and first of all, which characteristic this function is to have. So this property 2.2 is the key, right? I mean, and that's what we call this a suitable group function, right? I mean, is basically, it needs to be learnable, and it needs to map the data to a group element. So it's a map from the data to the group, such that, again, given that the invariant part of the autoencoder do their job correctly, this relation holds for all x. This relation is exactly what we saw before, right? I mean, given an input, x, this is the decoded output, and there needs to be a group element given by psi such that this equality holds. Means that the reconstruction task can be solved for all x in x, right? And we saw before that this needs to be equivariant in order for the loss to be invariant. But actually in the paper, we showed that, okay, a psi as equivariance is a little bit too strong, right? I mean, we want to characterize psi, and actually, like, strict equivariance is a little bit too much. And actually what we need, it's something a little bit more relaxed, which is we need G equivariance up to the stabilizer of the point we're considering. Stabilizer is basically, it's very simple, is the subgroup of the group G such that it acts trivially on that specific point, right? I mean, so the identity acts trivially on anything, but there might be a specific point in which there's a whole subgroup that acts trivially. That's the stabilizer. And basically the idea is follows, right? I mean, suppose that we have a G prime, which is not the identity, that acts trivially. It means that it maps X to itself. Now, full equivariance, strict equivariance would be that, okay, in some sense, psi commutes with G, right? I mean, so G would come out, right? I mean, so this wouldn't be there, right? I mean, okay, so psi of G of X is G of psi of X. But actually, that would be a little bit too strict, because this relation holds also if this is equivariant up to an element of the stabilizer, since this G prime anyway acts trivially on X. Okay, so basically this says that, okay, the collection of psi, right? I mean, which was part of our goal to really characterize which is the collection of suitable psi, is larger than just equivariant one is equivariant up to a stabilizer of a point. And the second key defining property is that, again, very intuitive, is that we need psi to cover all G, right? So we need some level of surjectivity. Again, we always factor the stabilizer because we saw that before. And that's very intuitive, right? But we can also have a look at maybe there's an idea of how we can see this, right? So let's take so this is the x hat is the canonical is the element that the decoder canonically decodes, right? I mean, so basically psi needs to learn to associate to this element the identity, right? Because if we actually start with the element that the decoder anyway decodes, we don't need to do anything, right? So psi needs to learn to map to this point the identity. Now, suppose that we transform our input by an element which is not in the image of psi, right? So not being surjective means that there's element that cannot be expressed as psi of something. But then, okay, so that's actually then very easy that we see that is in contradiction with this relation, because, okay, you know, this holds, right? I mean, this is this relation applied to x hat since psi is the trivial element, right? Which, but now we apply on this side, we apply the transformation rho of G. This is just the definition of X. Then, but X, so this needs to hold for each X, in specific for X. So basically, we just write this out, right? I mean, so basically, this relation, I just rewrote it here, where instead of X, where I put X, right? And now the trick is, okay, we saw that psi needs to be, again, minus the stabilizer, but needs to be equivariant. So G comes out. But now this, we saw that this is the identity. So this goes away. And if we compare this equality, this basically means that G is in the image of psi. Which means that, okay, so if this needs to hold for all X, then we need we need psi to cover all the group, right? Which is very intuitive, and this can be also shown fairly easy. So, okay, so these are the main two, if you want, constraints on the theoretical level. How do we, which kind of characteristic this group function needs to satisfy in order to be suitable. Now, how do we do it in practice, right? I mean, how do we actually solve these constraints? So, so how do our proposed construction actually assumes that, which is not the most general, but is one that works, assume that psi actually decomposes in a composition of two maps. The one map, mu, both map needs to be equivariant, again, minus the stabilizer, but we know what we are saying, right? I mean, this map contains all the learnable parameters, and maps the data space into an auxiliary space. And psi instead is a deterministic function. So this doesn't contain any parameter. So the key is this auxiliary space, which we assume to be a homogeneous space. Homogeneous space means that, you know, given 2 points, any 2 points in that space, there's a group element. So also here, homogeneous always with respect to a specific group, right? I mean, given 2 points, there's a group element connecting them, right? I mean, whichever 2 points we pick in Y, there's always an element that can connect them. So basically, the orbit of G in Y is, if you want trivial. There's only one orbit of G in Y. And now, in the map psi, now is defined as follow, right? I mean, so now we fix at the beginning of the training what Y naught is. Now, Y, will be the image of mu. So we start with x. We obtain a point y in y, right? I mean, mu of x. We know by construction that there's a group element connecting our fixed point y naught and mu of x, which is y. And this is exactly the group element returned by psi. And so, and given all this property, right? I mean, the fact that this is homogeneous can assure us that all the surjectivity and the property of equivariance is maintained through all of this, right? Because this map psi is by definition equivariant at this point, and so that basically in the paper we prove that this constructor satisfies all the constraints that we listed before. So now I pass the torch to Robin that will guide us into the practical application and in some example, unless there's some questions specifically on this part.
Yeah, and should we do questions in the end or
a question at the end? Either way, in any case, I'm gonna.
Yeah, so usually we, like if you're comfortable with that, we usually jump in and ask questions at any moment. And I know that there has been a question in the chat. I don't know if you've seen it from Fabrizio.
Fabrizio, do you want to say it yourself?
Yeah, sure. Hi, everybody. So I wanted to ask, essentially, it's very simple. How do you choose the canonical, or let's say the orbit representative with respect to which you predict the transformation with the encoder psi?
That's a good question, right? We don't. The question is that we leave the decoder choose. So it's a bit misleading saying canonical, right? I mean, because it's kind of suggesting what you are saying, that there's a preferred orientation, right? I mean, which is the one that we choose, and so on and so forth, right? The fact that we couldn't come up with like a more suitable name, right? I mean, but the idea is that we don't, right? We leave the decoder basically free to do its task, and we do not impose any preferred direction, right? I mean, and so basically, the decoder during training tries to solve its task, and at the same time, psi keeps transforming what the decoder decodes. And then at some point is the decoder that picks, okay, I decode things in this specific direction, but this is not preferred, right? I mean, maybe several run might give also different canonical orientation in some sense. So it's really free to the network to choose what this canonical is, which is kind of the cool thing. So basically, psi then needs to learn, given what the decoder chooses to do, then psi needs to learn, okay, so this is the canonical, and I need to shift things with respect to that, right? So is this combination of, so that's how the two parts interact, right? I mean, psi needs to understand, okay, what is the decoder canonically decoding now? Okay, I need to take that as the reference to do the right transformation.
Okay, thank you. So if in practice, so if might there be a problem during training if, for example, more than one canonical reference might be possible for the same input, for example, like maybe you put a batch in, and perhaps one specific instance in the orbit is chosen somehow emerges as canonical, but maybe you put another batch in of data, and it might happen that some other elements? Like, does this create some problems in the training?
But that never happens, right? I mean, because by construction, you are all the orbit gets mapped to exactly the same point. So for each orbit, you are guaranteed there will be only one, always the same, which might be changing during training because we are updating the weights, right? I mean, but you know,
right.
but actually you're guaranteed by construction that all the orbit will be decoded always in the same way because exactly you have an invariant encoder. So all the information about the group action is completely lost when you get to Z. So that's actually not an issue.
Okay, thank you.
Then
okay, so maybe okay.
I would maybe, or do you think another way to proceed is better? Otherwise, I would get to Francesco's question. No, Francesco?
Yes, thank you. Thank you for the presentation so far. Very interesting. So I have a few questions. So maybe if you think you're too long. So first of all, if you can do the same procedure sequentially, so move phi out. Second is how is related to augmentation. So because of course, if you present all possible combination, all possible group transformation, you can ask that they map with the autoencoder directly to one group. So is your approach more efficient? I suppose yes, but the third and last question is you mentioned some condition. So the existence of phi depends on the group, or does it always exist? Yeah, that was my question.
Okay, I think I go in reverse order since it's so what we show is exactly that the conditions that we gave and in the construction that we provided works for any group G, both continuous and discrete, right? I mean, so then if you want to code it, of course, you need some details that are group specific, right? You need to find an homogeneous space, which is homogeneous with respect to that group and all of that, right? I mean, so definitely then when you code, you're faced with, you need to think, and Robin will go in specific examples, so things will be very concrete, right? I mean, but the construction is valid for any group, and we will see example with continuous, with discrete, like permutation group, with products and all of that. For transformations, augmentation, yes, right? I mean, we are way more efficient, and both in training, because we don't need to actually we only need to show one element per orbit, right? I mean, since all these elements anyway are mapped to the same one, we actually need to show one element per orbit. So we are more efficient in training, and again. And Robin will show that actually also the embedding space we learn is actually better than the one that we can learn with the augmented classical autoencoder. And then you asked something about sequentially, which I'm not sure I understood the question. You said if we make psi not parallel but sequentially, and I'm not sure I understood the point there.
Yeah. So if you learn the transformation before applying the autoencoder.
Yeah, the thing is that we need to do at the same time because what I mentioned before, right? I mean, is the two tasks depend on each other, right? I mean, since delta is not fixed to it's not fixed to say, okay, you need to decode in this specific direction, right? I mean, delta is actually free to learn the direction it wants. So psi needs to be training at the same time because it needs to learn what the decoder is doing in order to solve the task. What you're saying, what one could do, but it's kind of not the point. Of course, if we say, okay, we take all the orbit, we order them in a specific direction, so that we force the decoder to learn a specific direction, then yes, I guess one can train psi separately. But then you don't need it anyway, right? I mean, if you're already, that's exactly what we want to avoid: manually ordering things such that the reconstruction task always can be done correctly, right? I mean, so it's really important that the two things are learned at the same time because they depend on each other.
Thank you. Thank you.
Okay, perhaps in the interest of time, I stop sharing, and then I'll be, anyway, happy to answer any further question at the end or during the talk.
Maybe also to manage your time, do you have to leave at 12? Do you have to leave at the hour?
I do not.
Okay.
I can stay longer.
Me neither, so I can also stay longer.
Okay, good. Then let's maybe have Tagir's question later on and continue a little bit so we have a nice wrap up in case anyone has to leave at the mark of the hour.
Great. So can you see my screen?
Yes.
Perfect. Okay. So yeah, like Marco mentioned, I will go through some examples for groups and data sets or data sources we basically applied the method to. And the first method or the first group and data was SO2, so the group of rotations in 2 dimensions, and we just applied it on this typical toy data set of MNIST, but MNIST in different rotations, so the rotated MNIST data set. And so like Marco mentioned before, right, basically main issue or the main thing we have to tackle is how to define psi for the particular group of interest. And here we look at the group SO2. And the idea basically, or our construction, so there might be other ways, but how we decided to define psi and how like it splits into psi and mu and space y is that we define this homogeneous auxiliary space y as the unit circle S1 in 2 dimensions. So basically this unit circle, and this y naught is just one point. We just chose the point 1, 0 at this on this unit circle. And the idea is now that we predict with our function mu, with our equivariant function mu, one point on this unit circle. For example, this point you can see here on the right. Wait, I will just put the laser pointer. No, you can probably see it better. And then Xai's job is basically just to construct then a representation of the group out of this predicted y. And as you can see it here already in the depiction, right, we can now just get an angle between this y naught vector and the predicted vector and define an angle. And with that, we can also define a rotation matrix basically by just taking the x and y elements of this predicted vector. And the cool thing now again is, since if we define y to be equivariant, then we know that if we rotate the input image, our predicted vector on the unit circle or the point on the unit circle will also then change equivariantly. And this then also means that the extracted rotation matrix, so the group representation, will also then change equivariantly. And so everything matches up in the end, which is then really neat. And so, yeah, and then, yeah, basically, so like I mentioned, this is how we then defined basically psi. And yeah, another cool thing maybe about the method is that this is just a framework, right? And you can use whatever neural network that has the right properties. So in this case, we need something that is E2 or SO2 equivariant. So we utilize this function, this equivariant steerable CNNs proposed by Weiler et al., basically to define the encoder by using the scalar outputs of such a steerable CNN And for psi, the group function predictor, we basically use the level 1 feature, so the vector feature output of the steerable CNNs. And that way we can basically parameterize our ether and psi utilizing these already existing CNNs. And for the decoder, there's nothing special we require, so we can just use a regular CNN. And then, as you can see here, right, the idea again is to encode in an invariant embedding and then reconstruct in its learned canonical orientation, and then basically apply the predicted group function. And if you look at the results, this is what we get, right? So here you can see in the depiction on the top, different MNIST images or the same MNIST image in different orientations, in different rotations. And this is basically the predicted canonical elements by delta. And you can see, like, as expected, it's always in the same orientation decoded, no matter what the input rotation is, because the embedding is invariant, and so the decoder will always map to the same canonical element. But then if we apply the group function that we predict psi, with psi, we see that we again align input and output, and they match up perfectly on each other again. And yeah, you can see that this works for all the different digit classes as well. And you also see that for some reason, the network then also picked the canonical orientation to be horizontally, in contrast to how humans might write digits. But this is just up to the network to learn. And if you reinitialize, this could also be vertical orientation, for example. But if you then look in the learned representations, you can really see, if you compare to a classical autoencoder, which gets basically different representation for a different orientation. You see that in the rotated MNIST data set, you see these different clusters for the same digit class, just because of the different orientations. And since our representations are invariant, you see that we have like distinct clusters for each class. And yeah, and this is exactly what we would like to see. And also, if you look at the like more in a detailed view, like in a downstream classification based on the representation. So this is just a like really simple KNN classifier, and we can see that our invariant representations perform much better than, for example, representations extracted by classical autoencoder. And we also compare to this approximately invariant quotient autoencoder that is better than the classical one, but does not perform similar to our method. And we also compare to, and this is also something that we often get asked, like what happens if we like fully equivariantly train the network, so have an equivariant encoder and an equivariant decoder, and just like symmetrize the embedding afterwards. And we also looked into this, and we really see that like the fully equivariant autoencoder with like in symmetrization performed afterwards does not perform as well as a network that is trained to be invariant from the beginning. Another example.
Sorry, I have a question, if you don't mind. It's actually a question from the chat that I find very interesting. Like, why all of the digits canonical representations seem to be horizontal, whether we would expect that they would be randomly horizontal or vertical, and why perfectly horizontal in the first case? Probably maybe because the image is less blurry that way. Like, do you have explanation for this?
So in my mind, it should be either horizontal or vertical, just because of the inductive bias CNNs have with their filters. So since you have like these 2x2 filters, they're kind of either horizontal or vertical just by gridding it. So I think that's one of the reasons why it's either vertical or horizontal. And here it just happened to be horizontal. And I think it makes sense to have like all the digits in the same orientation, just due to the I don't know, like the principal components of the digits. So if everything is aligned, you have like most variance along the first principal component. I think in this case, the horizontal axis. So this is like my hand wavy explanation for this. And
so somehow, like because the digits are longer in one direction than the other, and it kind of detect that length, it all aligns there.
Yeah.
Okay.
So this is what the decoder picks up and seems to be most works best for it. So there are also like digits that kind of have similar, like for example, like a 3 and an 8 makes sense that they are like aligned in the same direction, right? Because the 3 is like half an 8 kind of. Then you can utilize the same filters if you align it properly in the decoder.
Sure,
and
like
maybe
you can utilize the same filters, but in some sense you can say then the 3 and the 8 become more separable if you make them at 90-degree angle.
But yeah, but this is just happening in the decoder, right? So the decoder has to map to one canonical element. And I think then also for Psi, it's maybe easier to align basically all the digits in the same orientation, because then it gets easier to learn the to indirectly learn how to what kind of group action to predict. Right? So
yeah,
makes sense.
Yeah, makes sense. That makes a lot of sense. Also, like it surprises me that the 6 and 9 are so different in the embedding space. Something that even for humans, if you take a 6 and you invert it, well, maybe for some handwritings you see a good difference, but for some other handwritings you don't. So, like, how can you explain that the 6 and 9 are so well separated?
So actually, I get this question like every time I give the presentation why the 6 and 9 separate, and you can, I should definitely put the examples here because you can really see it. Like 6 and 9s, just because humans write them, they can be separated. So because it does, like if you write a 9, you write it differently than you write a 6, just because you write it in a flipped way. So you can in most cases, you can really see it by eye. And this is also what the network picks up. You can see actually that here there are some 9s that are actually in the 6 cluster. So I guess these are then the cases which are really, really similar and where the network cannot make a distinction. And maybe also like here at the intersection, you see like 6s there that are more similar to 9s. But in general, they are like, you write, like in MNIST, you often have 6s written in this way, while 9s have like a circle and then a straight line, and they are not like curvy as the 6 here.
Okay, makes sense. And one last question, like, do you have a mix of 90-degree and 270-degree rotation, or is it like, are they all like 90 degrees, for example, like?
So like in rotated MNIST, there are random rotations, and I think here we go through 45-degree angles for testing. And
no, I mean like the fact that like all the digits get represented horizontally instead of vertically, but that horizontal representation can either be 90-degree or minus 90-degree. Like, is there any observation about that?
Oh, I don't remember, but so I mean, you see it for these 3 examples. So you mean that the 6 could also be then, like the 9 could also be horizontally, but then flipped somehow, like?
Yeah, so the 6 and 9 could be the same thing, but one more straight and the other more cursive, right? But no, I think these are nice results. I'll let you continue the presentation.
Maybe a comment on this canonical, right? Because at the end of the day, right? I mean, we need to initialize the decoder somehow, right? I mean, we start with like an invariant embedding, and we need to somehow break the symmetry somehow in order for the decoder then than to learn, right? I mean, and that initialization probably is favoring one of those few options that Robin mentioned, right? Maybe with a different initialization, we would have all vertical. With another one, we would have all minus vertical, right? I mean, so there's also some, I'm not necessarily saying randomness, but there's some designing choice, which is not necessarily with the aim of picking one particular direction, but it turns out during learning that the network finds easier one orientation with respect to the other. So so that's another element that might influence why this and not vertical, for example.
Yes,
thank you.
And maybe just to mention this again, so this like one cool thing is also that we trained this whole thing just on MNIST and then evaluated here on rotated MNIST. So the network never saw like a rotated MNIST digit before. And this is just because by construction, we are invariant to the rotation of the input. So it doesn't matter if we put like rotated or not, or like non-rotated images in, which I think is also really cool. But yeah, I have other examples for other groups. So we also looked into symmetric groups, so permutation groups. And actually in the paper, we looked at sets of digits, but actually this work is kind of a follow-up, a more general follow-up for any group of this earlier paper of us from last year in Europe. And this was just about graphs, but like I mentioned, we generalized then this idea to any group. But here we basically had this works the same way. So we have some function psi that has to predict, in this case, a permutation matrix. And the idea here is, so I don't go too much into the details, but you can utilize something like a GNN, for example, apply it on a graph, and then predict for every node feature like a score, like just a scalar. And then what you can do is with the scalars, which since the GNN is equivariant, right? If you change two nodes, then the scores will also change, which the GNN is predicting. You can then use a sorting function basically to produce or like to extract a permutation matrix. So based on how the scores get sorted, you get a different permutation matrix to bring them basically in order. And then you can utilize this basically as psi to predict the permutation matrix to then again like realign a graph if you encode it permutation invariantly and then decode it in a canonical learned order, and then basically realign again node and adjacency metrics of the input and output graph. And then you can basically learn a permutation invariant graph level representation. And yeah. So these are then results of this method. So we utilize this for like in different experiments. So for example, for molecular property prediction, and we show that like this unsupervised learned representations, if we then extract representation of a data set with known properties, we can basically use them in a downstream model like a support vector machine to predict molecular properties, and they perform pretty well compared to these standard ECFP fingerprints. We also looked into like again representations of different graph families, and we can see that we have distinct clusters for different graphs from different families. We see that we nicely see a correlation between graph editing distance and Euclidean distance in this graph embedding space. And since we have a permutation invariant representation of the graph, we can also do something like graph interpolation. Like here, we interpolate basically between this graph, the start graph, and the end graph. And here, just for the coloring, what we did here, we colored all the edges that are only present in the start graph in red, and all the edges that are present in the blue graph, in the end graph in blue. And then we did this so that you can, during the interpolation, you can see that we step by step like remove red edges and add blue edges. And so we do here like a linear interpolation in the graph embedding space, and then always decode back into the graph space. And we can see that like smooth linear interpolations in the graph embedding results into smooth interpolation in the graph space, which I think is also a cool result. Yeah, then another experiment we did is with the group SO3, so rotations in 3 dimensions. And here we do something similar like in 2 dimensions, but here we actually have to predict 2 equivariant vectors in the on the unit sphere in 3 dimensions. So basically unit sphere, yeah. And so the idea is basically that we predict these 2 vectors, and then we basically make like orthogonal projections to construct like a new new frame of orientation. And this is basically how we can then construct the rotation matrix by this construction. And yeah, this way again we can utilize like 3D like SA3 equivariant networks to predict like these vectors that then can be utilized in our framework to predict rotation matrices and get like invariant rotation of SA3 invariant embeddings. And we applied this to this big famous Tetris data sets. And maybe just to mention this here we actually look at 3D rotations, also 3D translations, and since the different blocks in the Tetris shape are like exchangeable, we also have to be invariant to permutations of these blocks within one Tetris shape. And yeah, like I mentioned, you can utilize your favorite E3 equivariant framework like SA3 transformers or Pane, or you name it. And yeah, if you look at the results, you can, here we showed like input, output, and again, output plus rotation, similar to what we did in MNIST. And here we visualize basically the center of each Tetris block, and you can see that the input and output do not align, but once we apply the predicted rotation and translation and permutation, actually, we can see that the input and output align again onto each other. So we can reconstruct basically the Tetris shapes to a good degree. And if you then also look at Tetris blocks, which we like randomly noised, like added a bit of random noise to, so just to check like how the embeddings change under slight variation, we can see that again, these Tetris blocks, they cluster together, and we see like distinct clusters for each different Tetris block class. And yeah, we can, for example, also distinguish these 2 chiral shapes, like the violet and the green one here, in 2 different cluster. Yeah, and so this was more like a toy example for SA3, but we can also do this with molecular conformations. So here you can always, so I think these are QM9 molecules, which we auto-encoded into like 2 and from this 1 fixed size rotation, translation, and permutation invariant embedding. And yeah, you can see that the reconstructions are kind of accurate. And if you like transform this back into like a balls and sticks depiction, you can see that the conformations seem reasonable. And we also actually looked into how this can be utilized for pre-training, because we can now basically utilize this framework and pre-train like a SO3 SO3 equivariant network on this unsupervised pre-training, and then utilize this later for example, QM9 property prediction. And here we, for different fractions of data sets, we compared how the performance of a model trained from scratch compared to a pre-trained model that we pre-trained on a large set of geometries from, I think from the Geom data set this was. Yeah, here I have some more, just some more examples of molecular conformations, how they got reconstructed. And again, this is all like all these different molecular conformations, no matter of their size, so different molecular the number of atoms, they all get basically encoded to the same fixed size embedding. So we are also invariant to the number of atoms. And then as last slide, I think here, we also applied the method on voxelized data. So here on ShapeNet, and here you can see how we, for example, can out-encode these 4 different shapes to and from this rotation invariant embedding. And yeah, you can see that again, the input and the transformed outputs, they align again, and the reconstruction, they kind of makes sense. And you can also look into the representations, and you can see that the invariant embedding is better structured due to the due to the invariance to the rotations of the shapes. And yeah, with that, I'd like to thank you for your attention, and happy to catch up with the rest of the questions.
Okay, then let's do that. But before that, we have to say a huge thanks to you for this nice, no, not only for the nice presentation, also for the nice paper. Okay, but Tagi, I think, has a, he's asking if it's possible to generate now new molecules, for example, from your latent representations.
Yeah, sure. I mean, that's a really good question. And so this is now defined as an autoencoder, but we can easily redefine this as a variation autoencoder, and then train a probabilistic model that we can then sample from the embedding space. And actually, you can even do this already with the autoencoder, but then of course you don't have the nice properties of a variation autoencoder. And then you can see that you can sample different conformations that look energetically reasonable. So yeah, of course, you can use the trained decoder and then generate new molecules and new conformations of molecules.
And what would you now say is like the what would you now say is the most promising application of this that you expect?
I mean, like I mentioned in the beginning, my whole PhD was kind of about representation learning of molecules, and now I look here on this. Now we have like a powerful tool to have these representations that are also like invariant to certain symmetries, like for example for graphs. But like when I look at this kind of example, what we can now also do is, right, we can like get a representation, like a rotation invariant representation of a protein pocket, right? And we can now maybe match like a protein pocket representation with a ligand representation, and maybe even make a generative model out of it, and then generate, similar to what you did, like generate a compound inside a pocket, matching these representations. So I really like, or would like to go down this road, basically.
Yeah, so I'm a little bit sad not to see any results already in that direction, or any generated examples that did not come from our encoding already.
Maybe in the next paper.
Oh, that's a good teaser. If you want to advertise anything, we'd also be happy to hear that. Yeah. Anyway, Menghang or Menghang, I don't know how to pronounce it. How is the inference time of this work compared with equivariant neural networks, whose every layer keeps equivariance? Now, maybe you can just in general talk a little bit about time and complexity.
Well, I think this really then goes down to the particular network you use, right? If you use like your favorite equivariant network, then you will expect like a similar scaling in time.
So don't use E3NN if you want to save some time. And then what causes the disparity between the from scratch results and the pre-trained results on QM9? I think I don't quite understand the experiment.
So here the idea is basically that we either pre-trained a network on geom drug, like a huge collection of unlabeled geometries of molecules, and then we basically utilize this pre-trained network and then just trained it on a fraction of QM9 geometries with their associated properties, right? And then we compared this to a model that was trained, like the same model, but trained from scratch on the same fraction of QM9 properties. And then you can see that maybe as you would expect, that the pre-trained model already learned something about molecular geometries and can basically transfer this knowledge to the fine-tuning, basically.
Okay, then I guess, Alexander, great to see your face and your amazing hair. What's your question?
Thank you, Anis. Yes, I had a question, but first, thank you for the talk. It was very nice. My question targets molecules and 3D molecules, especially. I see you managed to reconstruct them very well. But do you need for that like a powerful encoder, or if you use like a model like SNET, which like completely forgets about torsion angles or bond angles, do you still manage to like get an accurate enough latent representation that so as to be able to reconstruct that properly? And maybe second question, because you can address it at the same time, do you need many like data augmentation samples in order to learn this invariant representation? Because the pipeline is a bit complex, so I wonder how you generalize to like bigger data sets and bigger molecules.
Yeah, so maybe to first, so SNET would be a problem, right? Because SNET is invariant and not equivariant, so you cannot really predict then the group function you need for the reconstruction. So, but you can use something like Pain, right? This is something we did and works pretty well. For the second question, like I mentioned before, so we don't have to do any augmentation. So you just need one sample per orbit, and this is all you need. So I think that's maybe also one like benefit of this method, that you kind of like all these other equivariant works, they kind of benefit from less training samples they need.
Oh yes, my bad. I thought you needed like still a few augmentations so as to be able to learn like the canonical representation that you have in the end. But it's really cool that you managed to do it without any data augmentation. It's really nice.
I really think you should not have called it canonical representation.
We are open to suggestions. I mean, we have been dealing with we just lack fantasy for names there, right? I mean, but yeah.
Okay. Okay, then I think we can get to Fabrizio's question.
Thanks. Yeah, thanks for the talk. It was great. So it's a bit technical, I think. If I understood correctly, if you work with graphs, the way you essentially predict a permutation matrix is you first predict the score for every node, and then this induces a sort, an ordering of the nodes, right?
Yeah.
So now, when you have symmetries in the graphs, for example, you have two nodes which are isomorphic because they are in the same orbit induced by the automorphism of the graph. You would always get the same score if you use an equivariant network, right?
Yeah.
So no.
Yeah, that's a really good point. And so in practice, how we handle this is just by adding some small random noise, and then basically you have like a slightly different score, and then the permutation would like still like decode one after each other, and then map basically in the permutation matrix then one after the other, like the element to this to the input element. But this is basically how we then handle that.
Okay, got it. So this is okay. What I want to say is this is in the extreme case, but if your encoder is not universal, you may have these problems even for nodes which are not isomorphic, right? But just equivalent, because maybe, yeah. So have you observed any impact of base?
Definitely, like highly symmetric graphs. Yeah, you run into issues there. So like in practice, like it works pretty well, I guess. But like if you really look at these edge cases, then you run into the problems, because this can basically then not be distinguished, and you, like in the case of a graph, then you have like you connect basically like the two symmetric nodes to like each other's neighbors, and because the network cannot pick up the difference there. You're right.
Okay. So I was wondering if ultimately, if you tried with encoders of different expressive power, for example, more than one WL, or like, to somehow mitigate this problem as well.
So like in this particular paper, we actually did not use GNNs, but transformers, and then also basically utilized edge features that encode the graph, like the shortest path as a distance. And this really helps also then, because you can, if you look into this, then this basically corresponds to an like to a higher level of WL complexity. So you can basically basically you're better than like a regular GNN in that case.
Right. Thanks very much.
Thanks.
Okay, well then, Tagir.
Hello, everyone, and thank you for the presentation. It was quite amazing and quite insightful. I wanted to continue the questions about symmetry in graphs. And have you ever seen, for example, if have you built even a chart or some analysis if there's high symmetrical graphs and you cannot reconstruct them properly?
Yeah, that's what or do you have more like a detailed question? Because definitely. I mean, if there's like a highly symmetric graph, then the reconstruction basically fails.
And I mean, sometimes it's also a question more just practical and technical. What is limitation, for example, for generation of molecular graphs? Because QM9 dataset consists of quite small molecules, and if, for example, with increase of size, you will also have you will lose the performance of reconstruction.
So for graphs, so in this example of this paper, for example, we use like not QM9, but look like drug-like molecules up to 32 nodes. So not like the largest graphs, but at least larger than QM9 graphs. And I mean, the larger the graphs get, the harder it will get to train, of course. But we still got like pretty good reconstruction accuracies there.
Okay. And maybe the last question is, have you, ever seen that if, for example, you change the order, like for the paper that we are discussing now, that if you change the order for the graphs, for example, or not exactly order, but translation or rotation, you can obtain different molecular structure. That it will be it will happen like to collapse. For example, you have benzene, and then you get just some other structure, for example.
You mean in the reconstruction, or?
Yes, on the reconstruction when you are decoding from the latent vectors.
So
due to a change in the order, I'm sorry.
Due to the change in the order, what do you mean with order in this case? Because here,
in this case, I would say that for example, if you rotate the structure, does it happen? Is it happened? It's just a theoretical question. Is it happen that you accidentally change the structure? due to the decoding, maybe not the perfection of the decoder or something like that. Maybe I'm not correct.
The thing is, if you rotate the inputs, the decoder is not affected at all, right? Because the input to the decoder is the invariant embedding, which stays the same if you rotate or translate the input. So by construction, you will not see a difference there.
Okay.
Yeah.
Okay, thank you.
Yes, I'm next.
Yeah.
So Tadija, you can.
Thank you for your talk. I have a follow-up question regarding the QM9 dataset. In my experience, I've run some like regressions on some of the properties in QM9 with these like reduced datasets. And I found that like even really simple encoders, like a few layers of a graph convolutional network without using the structure at all, they usually tend to get like low MSE like really quickly, even with like a small amount of examples. So I'm just wondering, like, because like some of these results, they seem like really low for training from scratch. And is that something about like the encoder used, or does it just way too easily overfit on the kind of subset, or yeah, just your experience with that?
Yeah, good question. I mean, maybe Turan is still in the room because I know that he performed the experiment, but yeah, you're probably right on the point here that we use the same encoder for the pre-trained and from scratch model, right? And this is definitely, if you train on this smaller fraction, probably like too over parameterized and you run into overfitting. But I don't know, like in this example, like how the data really looked like on that. But yeah, probably you can, this is not fair comparison. You can probably choose a better model for the same fraction of data that will perform like the same or better. That might be the case. But here the point is, right, that you can basically transfer. The method can also be, or might also be useful for unsupervised pre-training, like was seen in other cases like NLP, for example, where you can benefit from pre-training. So maybe this could also be a nice way to pre-train a network, but we didn't spend too much time into this. This was just like somewhere in the appendix, basically, at the moment.
Right. No, yeah, it's a very interesting idea. Definitely better than the pre-training procedure I was using for my thing. So
yeah, right. Because like I think one, like what people now mostly do is like denoise, right? Atom positions, and maybe this is like a better way to pre-train. But yeah, we will definitely look more into the details here. But thanks for the question.
Yeah, just to follow up there, like I also have experience with the very small fractions of QM9, and overfitting happens a lot, even with small models. I usually use small fractions of QM9 to test that my code is running, and not to actually train full models. But it's something that I experience. So the results here don't seem so bad to what I'm used to.
Okay.
And here I would like to add something like that traditional pre-training using VAE-like architecture on images, for example, has been done a lot by adding noise to the image, or blocking parts of the image, and things like that. And looking at the work that you have done, like we can also view this as a transformation to which the input is invariant, because in the end, an image, if you hide part of that image, as long as the main object is not completely blocked, then it remains still like the same class. So there is some sort of invariance to blocking object. And there is also invariance to noise. There is invariance to scale. There is invariance to rotation. And in graphs, like in graphs and in geometries, what are the invariants that we have to learn is actually these rotations and translation and other kind of groups that you have done into the paper. So this paper is like very novel, and I think it's one of the best way to really learn on these structures, because the same kind of augmentations that have been used in other fields which respect the symmetries of that particular object, like the symmetries of images, not symmetries like the invariance. And here you train also on the invariance, but on the invariance of graph and geometries, and it makes perfect sense for me. Regarding your question about denoising the position of atoms, I think it's still a good way. Like if you add a bit of torsion angle or a bit of change of the positions of the atom, it can still be a great way to denoise the molecule, because to pre-train on molecular graph, as long as the noise is relatively small, because in the end the molecule is not a static object. The molecule moves, it vibrates and everything, and it kind of helps the model to learn what is the actual local minima of energy. If you add a bit of noise, it's like, well, I'm still at the same local minima but vibrating around that minima, but I still have the same properties. So there is still something that is there is still something that can be used here that could perhaps be combined with the work that you have done also, because in the end you cannot add too much noise to molecules and hope that this is sufficient to pre-train. So I really think this is good work, and I'd be happy to try to maybe on larger data set and more relevant molecules than QM9 to see like how it would perform. And thanks a lot for the presentation.
Yeah, thanks for the comments. And I definitely, I'm not like, now I'm not super like yet I'm not super convinced that this like is the best way to pre-train. And like maybe just as a comment, like it's like maybe like this is not like appreciated directly, but it's really hard to do the autoencoding on larger, like especially on larger molecules of these conformations, because it's actually mostly not the rotation and translation which is hard to reconstruct, because this is really straightforward. The permutation is often the biggest problem, because that basically means that you have to aggregate all the nodes into one node basically, and then reconstruct all the nodes again out of this one global embedding. And we mostly struggle with that in doing training and optimizing network architecture. So this bottleneck makes the whole thing really really hard to train.
So here
also because in that case, right? I mean, for rotation and translation, the dimension of the representation that the group that you're trying to learn stays constant, right? I mean, you still want to predict SO3 transformation, which is like, if you want, the three main angles, right? I mean, or the translation, but with permutation, right? I mean, then the dimension of the representation just it grows linearly with the number of, so you actually there's really something which there's a scale problem, right? I mean, which then although theoretically no problem, right? I mean, then practically it, especially if you have, which often happens in molecule, large subsymmetries in the molecules, right? Lots of carbon atoms, lots of hydrogen atoms. So that you have this substructure of symmetry, which kind of confuses, basically the network. So so that's also, I guess, that also distinguish a little bit the permutation group with respect to the other groups, right? I mean, there's actually a scale issue there.
Right. So is permutation invariant something that you really need? What if you treat the molecules as point clouds in Euclidean space? And will that, like, did you try that? Do you think that learning on the permutation invariance is also something that was relevant to get better pre-training results?
Yeah, okay. I think it depends whether we need it or not. It really depends what you want to do, right? If you want a new art of descriptors, you know, then you want permutation invariant, right? You do want like a fixed vector of length, you know, 1024 or something that describes the whole molecular space, right? I mean, if you're interested in other properties, perhaps in conformer generations, right? I mean, then you might not care because you say, okay, I already know how many atoms I have in the molecules of that I want to generate the conformer for, the conformation for. Then you might not care. So I think it really depends what you want to do with these embeddings. And just for experience, if we don't pool, so if we don't if we don't aggregate if we leave out the permutation symmetry, it works really well also. I mean, I tried it on QMUGs, right? I mean, also with fairly high numbers of atoms, and then it works like a charm, right? I mean, so that's really the bottleneck here. And I think it really the really
reconstruction
depends.
works well, right? So
yes, sorry, yeah, I'm talking about the reconstruction. Yeah, the reconstruction works works well. Yeah.
But the thing is, you cannot use the embeddings because you don't have like a molecule or like graph level representation. Because if you then aggregate, you basically have then node representations, and you can then aggregate them by concatenating them, for example. But then you have like dependent on the node like indices, you have like a different graph embedding. Like if you permute the atoms, or if you average them like after the training, like we showed before also with MNIST, you don't get the same representative power in downstream applications or usage of the representations.
Sure, but you can always have like a deep set that is learnable. So you fix your node level representation, you learn the deep set, and after a few epoch, you unfreeze the first learned representation. So
then you need supervision of like a non-unsupervised supervision, but you need some kind of labels to do like supervised learning, right? So this is really like, these are the two options you have. Like you either do supervised learning with something like deep set, or you do unsupervised learning, but then you have to basically tackle this symmetrization part and reconstruct, like in the case of an autoencoder, reconstruct from something that is invariant. So this is basically the issue.
All right, thank you. So let's jump to Meng Hang's question.
Oh, thanks both for the great talks. I have actually follow-up questions on the previous my previous question on the inference time. So I'm thinking if the final task of our, let's see, the machine learning like network or autoencoders is to predict it like forces acting on the atoms at each molecular dynamic step, then I'm thinking this structure, your work can actually learn the invariant and equivariant representations, and then just put into a neural network that does not necessarily become equivariant. So just put like a vanilla neural networks, and you can do prediction of force and energies. Or you can use like pure geometric data from molecules and use supervised learning like E3N to like or equip to predict the force and energies. But the neural network itself is equivariant. So I'm just wondering for this two approach, like one is do the data processing more and use less time on the inference, but the other is use less time on data processing, but use longer time on the inference. I don't know in summation which approach might give a better performance in terms of time.
Can I clarify first a little bit? I don't understand why there's a difference in time, right? You still have to do your forward pass through E3 and N if that's what you choose to use as your encoder.
But what I'm thinking is that if this autoencoder can already represent the geometric data into a descriptor that is invariant or equivariant, then your next step, like your neural network, doesn't need to be equivariant.
Yeah, but still you need to put it into you need to run your E3 and N to get your descriptor that is invariant or equivariant every time step in your MD simulation as well.
Yes, but I mean, but that part is on inference part. You don't need to pre-process the data, encode them into the descriptor that is invariant or equivariant. But for this work, you can actually do the data processing first, learn your invariant equivariant representation, and just do the simulations on those descriptors.
Okay, I'm not sure what you mean, but maybe the others do.
I think I have the same struggle understanding this. So yeah, so doing inference, you still have to run the encoder, right? But your point is that you, like, before you run the simulation, get all the descriptors out, like as a data pre-processing step, but then you cannot run like simulation, right? So because
but then the prediction parts will be done on like a vanilla neural network, not necessarily an equivariant neural network.
Yeah, but still for each, like if you do the simulation and you update the positions in your of the atoms in your MD simulation, then on the new updated positions, you still have them to apply the encoder to extract the invariant descriptors, right? And then you then have to run the inference through the encoder, which might be like an E3 and N network or whatever.
Oh, I see the points. Okay.
Good.
Okay, thanks.
Okay. Yeah.
Nice, that's cleared up. All right. Then I think we have no more questions left, unless someone interrupts me in this now. And then, yeah, let's have a last, or do you want to have some last words?
Us? Maybe just, again, like, thanks for hosting us. It was great. And also like all the questions. I mean, we're now at like nearly an hour question. That's really great. So thanks for the interest and the questions.
Also from my side, not only a thanks to you for the presentation and paper, but to all the questions from Alexandre, from Fabrizio, and everyone who I'm forgetting. All right, then I think we can.
Thank you so much from my side as well.
Okay, I really liked that paper. I hope you liked it too and learned as much as I did from this introduction and this talk, this discussion. And if you want to learn in future sessions, then find the details in the description. See you.